Hello, young chemists. What is up? Mr. Rosen here. Today we're going to talk about partial pressure problems, partial pressure of gases. And the thing about partial pressure problems is there's really not like a one-size-fits-all approach. It's not like, the ideal gas law where you have PV equals nRT and you just use the same equation every time and you plug in, 4 of the 5 variables and you solve for the other. There are a lot of different partial pressure styles, but there's a couple of key concepts, and if you understand those concepts, then you'll see that we'll apply them in different ways. So, partial pressure is the pressure that is exerted by a gas in a mixture of gases. So when you have multiple gases in a container, each gas in the container will bounce off the container walls and will exert some pressure. Okay, so as it says here, the partial pressure of a gas is the fraction of the total pressure that's contributed by one gas in the mixture. Okay. Stated another way, the partial pressure of a gas is the pressure that the gas would exert if it was in the container by itself. And we've talked about John Dalton in the past, but he proposed a concept related to partial pressure that is the total pressure exerted by a mixture of gases is the sum of the pressure exerted by each gas in the mixture. So this is called Dalton's law of partial pressure. And here you can see it says P total equals P1 plus P2 plus P3 and so on, where P total is the total pressure exerted by all the gases in the mixture. And then P1 is the partial pressure exerted by gas number 1. And P2 is the partial pressure of gas number 2, and so on. The idea here is each gas in the mixture exerts some pressure, and the total pressure is the sum of the partial pressure of each gas in the mixture. Okay, now you can also take that same idea and solve for the pressure of each individual gas in a mixture if you know the total pressure and how many moles of gas are present. So this says that the pressure of a gas, X, is equal to the total pressure times however many moles you have of that gas, gas X, over the total number of moles. That is, if you take the moles of that gas divided by the total number of moles, that is the fraction of the total contributed by that gas. So that's the fraction of the total contributed by that gas. So we're going to do some example problems of each of these. It's also good to mention a couple of big ideas here. One of them is that the total number of moles of particles is what's important, not the identity of the particles, so we don't really care what the identity of the particles is. And the other thing that is good to know when we talk about partial pressure is this idea of collecting a gas over water. So it says pause to explain lab technique. Here you can see there's a sample that's being heated and it gives off some oxygen gas. The oxygen gas goes through the tube and then it comes up out this end of the tube, and the only place for it to go is into this container. And as the gas builds up, the water that's displaced just flows back into this little dish or a trough below. I did this as a demonstration in class. We've also done a lab using the technique of collecting a gas over water. But what's important to realize here is whenever you collect a gas over water, you have the gas that you're collecting in here, but water evaporates to a gas as well. So you actually don't just have oxygen in here, you actually have oxygen gas and water in the form of a gas, water vapor. So this is actually a mixture of gases. And each gas exerts its own pressure, right? So the total pressure of gas exerted the total pressure exerted by the gas inside this is the sum of the pressure given off by the oxygen and the water. The pressure given off by the water vapor is what's called the vapor pressure. And if you're interested in studying the gas by itself, you regularly have to subtract the vapor pressure from the total pressure in order to get the pressure of what they call the dry gas, meaning the gas without the water vapor. Okay, so we're going to do some problems related to that and using actually the ideal gas law. So we're going to have three different styles of problems here, all partial pressure related, all related to this idea that the total pressure is the sum of the pressure exerted by each gas in the mixture. Okay, so I just explained this, right? The total pressure is the pressure of the gas plus the water vapor. And if you want to know the pressure of the gas by itself, you must subtract the vapor pressure from the total pressure. So the first question says, a 0.5 liter sample of neon gas is collected over water at 25 degrees Celsius and 780 torr pressure. What's the volume of the dry gas at STP? So STP is standard temperature and pressure. Now, notice it says the vapor pressure at that temperature is 23.8 torr. So the first thing we have to do is subtract the vapor pressure from the total pressure to find the pressure of the dry gas, the gas by itself. So that means we have to take 780 torr and subtract 23.8 torr, and that's going to give us the pressure of our dry gas alone. So 780 minus 23.8, we get 756.2. That's now in torr. Okay, so 756.2 torr. That is the pressure of the dry gas alone. Okay, that's the pressure of not the mixture, but just the gas. So we subtracted the water vapor. Now we're going to use the ideal gas law after, of course, we do some conversions. So we need our pressure to be in atmospheres if we're going to use the ideal gas law. So this is 756.2 torr, and 1 atmosphere is 760 torr. So we're taking this divided by 760, and you can see that's going to be a number that's very close to 1. That's 0.995 ATM. So now we're going to plug everything into the ideal gas law. All right, so our pressure is 0.995 ATM. Our volume is 0.500 liters. N is what we don't know. R is the universal gas constant, 0.08206. This is liter atmospheres over Kelvin mole. And temperature needs to be in Kelvin. Now, our temperature is at 25 degrees Celsius, so that's another conversion. So up here, I'll say 25.0 degrees Celsius plus 273 is 298 Kelvin. So 298 Kelvin goes here. Now you might be wondering, hold on a second, why am I solving for moles of gas when this question is asking what the volume of the dry gas will be? Well, the problem is we have a certain volume at a certain temperature and a certain pressure. So we need to figure out how much gas we have. And once we know that, we can solve for what its volume will be at a different set of conditions, right? Standard temperature and pressure is not this temperature and it's not this pressure. So we're going to solve for moles. To do that, you have to get n all by itself on one side of the equal sign, so I'm going to divide by 0.08206. Uh, 298 Kelvin. These will cancel, leaving you just with n on one side. Whatever you do to one side, we do to the other, so this is going to get divided by 0.08206. This is 298 Kelvin. So really, to solve for n, it's PV divided by RT. So on my calculator here, I still have P in there, so I'm going to multiply that by 0.5. Now, this number gets divided by the product of R and T. So it's important that when you press divide, you don't just say divided by that number and then hit multiply by that number. You actually have to do order of operations. So open parentheses, 0.08206 times 298, close parentheses. And we get 0.02. We're going to go to 3 significant figures, so it's 0.0203. That's N, which is moles. Okay, mole. So we now know how many moles of gas we have. The final step is to know what volume that will occupy at STP. Well, at standard temperature and pressure, 1 mole is 22.4 liters. So we can simply take our number of moles and convert it to liters using 1 mole is 22.4 liters. That's the molar volume of a gas. Now you could plug this in, N as N, you could plug it into the ideal gas law, where P is 1 atmosphere and T is 273 Kelvin, but you would end up getting the same answer. Moles will cancel, and you'll be left with your answer in liters, which is about 0.456 liters. So if we sort of just compare what we have, what it's saying is this gas, when we collected it at this temperature and this pressure, had a volume of 5 liters. They wanted to know what the volume would be at a different set of conditions. So we had to solve for moles, and you can see that at a different set of conditions, the volume is a little smaller. We're going to do another one of those problems. All right, I'll do this one a little bit quicker. So you have a volume collected over water at a certain temperature and pressure. What's the volume of the dry gas at STP? And they give you the vapor pressure. So again, this is a mixture of gases because it's collected over water. So we're going to have to take the total pressure, which is 770 torr, and we're going to have to subtract 23.0 torr. Oh, oops, sorry. At 23.0 temperature, the partial pressure is 21.1, so I apologize about that. This is 21.1 torr. I wrote the temperature down by accident. And that will give you your pressure of the gas by itself. Okay, so this is the aspect of it that's related to partial pressure, is that the pressure of the gas is only part of this. The gas contributes 748. I'm sorry, 748. Actually, with rounding, that's 749 torr. Sorry that this one's coming out so messy. We took the total pressure and we subtracted the vapor pressure, and we got the pressure of the dry gas by itself. Okay. We also will need to turn our temperature into Kelvin. So this plus 273. If we add 273 to this, we get 296 Kelvin. Okay. And our milliliters needs to be converted into liters, so we divide by 1,000, and that gives us 0.0640 liters. Okay, now we're ready to plug everything into the ideal gas law. So our P, actually we're not. We still have to take torr and put it into atmospheres. Okay, 1 ATM is 760 torr. So that's 0.985 ATM. That's in atmospheres. Now, after all of those conversions, we're ready to actually plug it into the ideal gas law. So 0.985 ATM. Volume is 0.0640 liters. N is what we don't know. R is 0.08206. That's liter atmospheres over Kelvin mole. And then temperature is 296 Kelvin. So we solve for N. We're going to divide by RT. So we're dividing by 0.08206 over Kelvin mole times 296 Kelvin. That will leave us with N on one side, which is going to be in moles. Whatever we do to one side, we do to the other. So this is divided by 0.08206. So if we do this, if we take our pressure 0.985 times 0.064, we get a number that gets divided by the product of 0.08206 times 296 close parentheses, and we get our number of moles, which is 0.00260 moles. And again, this problem is asking what the volume will be at STP. So 0.00260 moles, 22.4 liters is 1 mole. So we just take that times 22.4. We get 0.0581 liters. That is your final answer. So this is basically like an ideal gas law problem, but you have to do some conversions and you have to subtract the partial pressure from the total pressure to get the pressure of the dry gas. Okay, that's the gas without the water. Now, there are other varieties of partial pressure problems. You also have ones where you're given mixtures of moles of gas and you are solving for the partial pressure of an individual gas. So this one says, a mixture of 4 moles of hydrogen and 3 moles of nitrogen are in a container with the total pressure of 745 torr. What's the partial pressure of each gas? So the important idea here to understand is this is the total pressure, okay? That amount of pressure is determined by how many moles of gas you have in a container. So like, if you have 5 moles of gas in a container, they give you this pressure, right? In this case, we have 4 moles of hydrogen and 3 moles of nitrogen. So that's a total of 7 moles, right? 7 moles total end up giving you a pressure that's 745. This question's asking you, of that 745 torr, how much of it comes from hydrogen? And how much of it comes from nitrogen. So the pressure of an individual gas is the total pressure times the number of moles you have of that gas divided by the total number of moles, right? So like in this case, 4 of the 7 moles are hydrogen. So if we take 4 moles are hydrogen over 7 total moles, this is moles total, that number that you get, right? So if we take on our calculator, if we take 4 and divide it by 7, that number, which is like 57%, right? That is the percent of the total torr contributed by hydrogen. So if you take that number times the total, 745 torr, okay, so in the calculator here, I'm just going to say times 745, this number is how many torr are contributed by that gas. So I'm just going to round to 3 sig figs here, and that is 426 torr. Okay, and this is for the partial pressure of hydrogen. So I'll say P hydrogen equals. Now, because there's only 2 things here, if you wanted to figure out what the other one was, you could just simply take 745 and subtract to this, and that would give you the pressure of the other gas. But we'll write it out here. So pressure of N2 is 3 moles of the 7 moles total times 745, and we'll see what we get here. So 3 divided by 7, it's like a little less than 43%, times 745, so about 319 is contributed by the nitrogen. And if you add these 2 numbers together, what you'll get is 745, which is our total pressure, right? So that total pressure, of that total pressure, some of it comes from hydrogen and some of it comes from nitrogen. And you can see that more comes from hydrogen than nitrogen, and that makes sense because it's more hydrogen than nitrogen. Right? So this is a partial pressure problem when you're solving for the pressure of individual gases based on moles and total pressure. Okay, so we'll do one more. It says a mixture of 2 moles of hydrogen, 3 moles of ammonia, 4 moles of carbon dioxide, and 5 moles of N2 exert a total pressure of 800 torr. What's the partial pressure of each gas? So if I wanted to know what is the pressure of hydrogen, pressure of H2, it's 2 moles of, how many moles do we have total? 2 plus 3 is 5, plus 4 is 9, plus 5 is 14 moles total. So we have 14 moles total. So 2 out of the 14 come from hydrogen, right? So 2 divided by 14 gives us this. It's about, pretty close to 14% of the total pressure comes from hydrogen. So we're just going to take that times the total pressure, which is 800 torr. And in here, I'll just leave in my calculator, so times 800, we get about 114 torr. That's the pressure contributed by the hydrogen. Then we have the pressure contributed by NH3, right? And that's 3 moles of the 14 moles times 800, right? So this time, it's going to be 3 divided by 14 times times 800, and we get about 171 torr. So of the 800, about 114 comes from hydrogen, about 171 comes from ammonia. The pressure of the CO2 is 4.0 moles of the 14 moles times 800 torr. So 4 divided by 14 is some number times 800, about, we're going to round here, 229 torr. And again, if you wanted to find the other one, you could just add these up and subtract it from 800 to get the remaining one. But we'll write the other one out too. Pressure of N2 is 5 moles over 14 moles times 800 torr. So on our calculator here, 5 divided by 14, about 36% almost, times 800. Okay, so that is 286 torr. So that's the pressure contributed by each. Now on my calculator, if I wanted to, I could say, all right, let's see, 114 plus 171 plus 229 plus 286, and what do we get? 800. Okay, now there might be a little difference because of rounding, but that's the total pressure. They all add up, right? The total pressure is the sum of the partial pressure of each gas in the mixture. So it's an easy way to check your work like that. All right? The final style of partial pressure problem is when you have what are called flasks or multi-flask vessels, just containers that have mixtures of gases or gases in each flask, and then you open the valves and you get the gases all mixed together. So we have 3 flasks or bulbs here, and they have different gases in them. And this describes the volume of each. It also gives you the pressure. In this case, it says the volume of each flask are as follows. So CO2 is 2 liters. So this one is 2 liters. H2 is 1.5 liters. So this is 1.5 liters. And then the argon is 3 liters. So this is 3 liters. So we have the volume of each of them. It says if the pressure of the CO2 is 3 atmospheres before the valve is opened, what will be the partial pressure of the CO2 after all the valves are opened? Now, this is actually just really, in a sense, it's a Boyle's law problem. Boyle's law is P1 V1 equals P2 V2. So for CO2, our starting volume, P1, is 2 liters. And our starting pressure is 3 atmospheres. They're asking you, when all the valves are opened, what will be the partial pressure of CO2? What will be P2 when all the valves are opened? Now you might be wondering, well, what's the new volume going to be? Well, think about this. Right now, this container is 2 liters. When you open this valve and you open this valve, it means that this gas is free to go into any part of this whole vessel, right? So you need to know what the total volume of this whole thing is once the valves are opened. So this is 2 liters. This is 1.5 liters. So if you add those together, you get 3.5. And this is 3. So if you add this all together, the total volume, right? 2 plus 1.5 plus 3. If you add those all up, the total volume is 6.5 liters, right? 6.5 liters when the whole thing is opened up. So V2, once all the valves are open, is 6.5 liters. So we can solve for the pressure of the gas, right? We're solving for P2. We divide by 6.5 liters. Sorry about the bell. That'll cancel. That'll leave you with P2. Whatever we do to one side, we do to the other. 6.5 liters. Liters will cancel, and you're left with your answer in atmospheres, which will be the pressure of the CO2, the partial pressure of the CO2 once all the valves are open. So 3 times 2 is 6 divided by 6.5 gives you 0.923 atmospheres. Okay. So that's the pressure contributed to the total by CO2 when the valve is opened. Now we're going to do a final problem. I know this has been a long video, but this problem says, okay, we have 2 bulbs, two sides of the container, and there's a valve between them. It's a little bit hard to see, but it says the pressure and volume of each. Now, the question says, when the valve is opened and the gases mix, what is the partial pressure of each gas in the mixture, and what will be the total pressure exerted by the gas mixture? So the first thing we should do is convert one of our pressure units into the other, because this is torr and this is atmospheres. I think we'll just convert torr to atmospheres. So 475 torr, 1 atmosphere is 760 torr. So if I take 475 divided by 760, I get 0.625 ATM. So we'll just use that instead, 0.625 ATM. Now we have all of our units as they should be. So we know the starting pressure and volume of each of them. To find the partial pressure of each gas when the valve is opened, it is, again, just like a Boyle's Law problem. So if I want to know the partial pressure of hydrogen, it's going to be P1 V1, right? I'll just jot this here. P1 V1 equals P2 V2. So the pressure of hydrogen is 0.625 ATM. The volume is 2 liters. P2 is what we're solving for, and V2 is what the total volume will be once this is open. So this side's 2 liters, this side's 1 liter, so the new volume will be 3 liters. So I'm going to solve for P2. And if I do that, I will get the partial pressure of hydrogen. So that's 0.625 times 2 divided by 3. That's 0.417 ATM. So this is the pressure, partial pressure of hydrogen when the valve is opened. Okay. Now I'm going to do the same thing over here for the pressure of nitrogen, which is going to be our starting pressure, 0.200 ATM, our starting volume, which is 1 liter. We're solving for P2, and the ending volume is 3 liters. So we divide by 3 liters, cancels to give us P2. Whatever we do to one side, we do to the other. Liters will cancel, giving us our partial pressure of the nitrogen, which is our calculator here. We're going to have 0.2 times 1 is the same number divided by 3. You get 0.0667 ATM. So at this point, we have the partial pressure of hydrogen and the partial pressure of nitrogen, right? So we have the partial pressure of each gas in the mixture. But it asks you for what the total pressure is, okay? And the total pressure is the same as the sum of the partial pressure of each gas in the mixture, right? P total is equal to P1 plus P2 plus P3 and so on. Now we only have 2 gases here, so the partial pressure contributed by the hydrogen is 0.41 atm, and the partial pressure contributed by the nitrogen is 0.0667. So if we add those together, we get our P total, which equals, let's add those together. We're going to add together 0.417 plus 0.0667, and we get 0.484 atm. That's the total pressure inside the container once the valves are opened. I know this has been a long video. Like I said, there's a lot of different style of problems for partial pressure, but they all rely on the idea that the total pressure is the sum of the pressure of each gas in a mixture. And if you know the total pressure and how many moles you have, you can also solve for the partial pressure of each gas. All right? So this has been a video on partial pressure of gases. Keep working, keep studying. Hopefully this was helpful. Good job.